Yeah, we have a minute.
Yeah. Yeah, this time you will talk about some brief publications using in content codes. I guess this what you most.
I probably don't have time to mention that.
Okay. I thought you will, but
yeah, but I don't know. We'll see.
Ja. Nei, jeg får sånn ja, jeg lurte på om du bare kom inn en særen. Ja, det kunne jo hende. You're doing the cycling thing?
Yes.
Yeah. Is it today? Tomorrow?
Yeah, not today. No. I hope not.
You hope not. So how long are you planning to? How much time do you think it'll take?
I am for less than 7 hours.
Yeah. That's a long trip.
Yes.
Yeah.
Okay, we are a couple of minutes past, so maybe we should start.
yeah. Yeah. So let's start. So I will do some brief openings to introduce the data line. So yeah, I need some notes. It's very pleased that we have a data line join us virtually today. So this talk was motivated by us because we IEEE young professionals in Norway need to do some speaks within IEEE such that can attract more people, more audience to join this big community of IEEE every year. So I met Dr. Lai when I was interested in content stabilizer codes a few years ago. And Dr. Lai received his PhD from the University of Southern California, which is one of the top universities in USA. His research interest in coding and the information theory and the fault-tolerant quantum computation, quantum algorithms. So he's the one, or maybe the only one I know that, I mean, personally, I know that he knows quantum and the information theory, which actually is good for me, actually. And he's also doing quantum cryptography. So I think if he has time for people who are doing crypto, actually you can discuss anything with him. And then he just mentioned that he also doing some post-quantum crypto, actually. So yeah, so feel free to discuss with him. So now we want to join our forces to do something about quantum privacy and the coding theory. So I believe that you can easily find his CV by Google search. Then I won't tell too much. So let's just start our talk. Yeah, thanks.
Thanks, Ching-Yi. Thank you for the opportunity to give a talk here. I've never been to Norway, so I hope I have future opportunity to visit you guys there physically. Yeah. Okay. So today I'm going to give you a tutorial talk about fault-tolerant quantum computation. So in the first part of the talk, I will briefly introduce the basics of quantum mechanics and show you what we can do with quantum computation. Okay, and in order to implement a quantum computer, we need to implement some kind of quantum circuits, but in the quantum scenario, all the error rates, or you can consider some physical decoherence rates are very high. Compared to the classical computers, a quantum computer is very difficult to build because the error rate are very high. So we need to consider this kind of fault-tolerant schemes. Okay, and then I will briefly mention current stages of the quantum computer. Okay, I will tell you something about the current experiments. Okay, and I wish I have time to mention my recent results here. There are some 3 papers here recently, because we want to build a quantum computer, and a quantum computer to have a fault-tolerant quantum computation, the quantum information need to be protected by some quantum error codes. Okay, we need error codes like the classical case, and you know, from classical coding theory, a very important code family is the low density parity check code, LDPC code, right? So we want to have some benefits from this low density parity check codes. Okay, and you know, LDPC code has a very good and efficient decoder by variable propagation, and want to extend those ideas to the quantum scenario. Okay. Okay. And yeah, this is one of my favorite sunrise in Taiwan. I hope you have the opportunity to come to Taiwan as well. Okay. Okay, so this is my outline. First, I will introduce quantum computer and mention some current development in the world, and tell you about the idea of large-scale fault-tolerant quantum computation. And finally, if I have time, I can tell you something about error codes. Okay. Okay, yeah, we'll see. Okay. So let's take a quantum leap here. Actually, this is a photo from our commencement this year. Okay, take a quantum leap. Okay, this is a photo about computers you have seen. Okay, from the ancient computers, the EPCAs. Okay, or a calculator, personal computer, tablet, or some supercomputer. All you have seen here are classical computers. Okay, because there is no quantum effects within these experiments. Okay, even you have a array of supercomputers, yeah, it's still classical computer. Okay, so what is a quantum computer? It's a type of machine that can exploit quantum effects so that you can efficiently solve some problems that classical computer will be able to solve within a reasonable amount of time. Okay, this is my my definition of a quantum computer. Okay, so let's briefly see what is a type. What does a quantum computer look like? Okay, this is Google's quantum computer they announced in 2020, or maybe by the end of 2019. Okay, this is their quantum computer. This is a superconductor quantum computer. So you see there is a chip on the right hand side, right? This is a chip. And this chip is on the bottom of the this big machine. Okay, there are many wires here. They are used to control this chip, and then the chip is only a small tiny part at the bottom here. Okay, can you see that? Okay, and they need to put this machine within a huge refrigerator, because this machine only works around 3K, something like, or below 3K. Okay, so okay, so this is a quantum computer. Okay, so I will explain how it works. Okay, if you have any questions, you can ask me anytime. Okay, So let's start with some introduction to content information. This is the most simple context I can have for you. This is content information for babies. Okay, you see this. Chris Ferry, a professor at the University of Technology, Sydney, he wrote a bunch of books like this. Okay, so if you want to study content information, you can start from this kind of book. But this is a page from the book. I have one of this book. Okay, but these books are very easy. The context you have already known from maybe high school. Okay, so what do we learn actually in graduate school is this one. Basically, we will use this book, Niels and Zhang's book, Quantum Computation and Quantum Information. Okay, so the basic idea is that quantum mechanics is a linear theory. So all you need to understand quantum mechanics is linear algebra. Okay, you only need linear algebra and some probability theory, then you will be able to understand how quantum mechanics works. Okay, and you are able to learn these quantum algorithms or quantum cryptography. Okay, so the first idea is the quantum state. Okay, usually we'll use this kind of notation. This is called a kit. Okay, a single qubit pure state psi is a unit vector in complex number. Okay, two-dimensional complex number. So ket is a unit vector, and we have, because this is a two-dimensional vector space, we can choose a basis ket 0, ket 1. Okay, and because it is a unit vector, so the amplitude of this 0 and 1, they have to sum to unit. Okay, so this is a unit vector. So, and this is a continuous vector space. Okay, this is the complex numbers. On the contrary, in the classical world, a classical bit is simply a 0 or 1, right? In a binary field, 0 or 1. Okay, so you may have seen this. Okay, I think everyone has heard about Schrödinger's cat, right? Because from movies or TV, you have heard about Schrödinger's cat. Classically, a cat can be alive or dead. But for a Schrödinger's cat, it can be in a superposition of the state of alive and the state of dead, right? So this can be represented by this mathematical description here. Okay, and we have the state of alive and the state of dead. Okay, and this amplitude here represent the probability at this state. Okay, so this is a superposition of the state of alive and the state of dead. Okay, but if you using the idea of linear algebra, this is simply a vector in a two-dimensional complex vector space. Okay, so this is a Schrödinger's cat, and this is a classical cat. Okay, so the important idea here is that in the quantum world, we allow the superposition of states. Okay, superposition. This is the first important thing you need to remember. Okay, so next, in the one qubit case, we have ket 0, ket 1. In the two qubit case, the basis extend to read here. We have two qubit in 0, 0, 0, 1, 1, 0, 1, 1. Okay, and again, psi need to be a unit vector, so these amplitudes will sum. The amplitude square of this values sum to 1. Okay, we have to do this normalization. So you see, in a two qubit case, there are four bases. Okay, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so in the n-dimensional case, in the n-dimensional case, sorry, in the n-qubit case, we will have 2 to the n bases. Okay, the basis starts from 0, 0, 0, 0, 0, 1 up to 1, 1, 1, 1, 1. Sorry, I got it from. 可以不要接吗？ sorry, I got a phone call. Sorry. So you see, in the n-dimensional case, we have 2 to the n bases, right? So the dimension of the n-qubit state space is 2 to the n. So it's exponential in n. Okay, so it's very the speed of the growth is very quick in the number of qubits. So can you imagine how many atoms are there in the universe? Maybe some of you know the answers. Okay, how many atoms in the universe? Okay, it's around 10 to the 80 atoms in the universe. 10 to the 80. What does it mean? So if I have a quantum computer with like a 300 qubits, if I have a quantum computer with 300 qubits, then the dimension of this quantum space is 2 to the 300, and that would be larger than this number, right? So it means that if I have a quantum computer with 300 qubits, I can there are something I can represent in this quantum computer, but that is beyond the capability of any classical computer, because the number of atoms in the universe is this much. You cannot use this number of atoms to represent a larger numbers. Okay. So if I have like 1,000 qubits, I can do incredible things. Okay. So this is another potential of quantum computing. So the next idea is quantum evolution. From quantum mechanics, we know a quantum state is a unit vector in the in complex numbers. So the evolution of a quantum state is described by a unitary operator. Okay, you can imagine it's just a matrix evolution. Okay, and the quantum algorithm can be implemented in a quantum circuit like this one. Okay, consisting of quantum wires, single qubit gates, 2 qubit gates. Like it's just like the classical case. Okay, here each wire here represent a qubit. Okay, so I have 3 qubits here, and there are some quantum gates here, like this Hadamard gates, and this is a 2 qubit gate, control NOT gate. Okay, something like this. So any quantum computation can be implemented by a universal set of elementary gates within with arbitrary accuracy. Okay, for example, this gate set here, H gate, S gate, C NOT, T gate. If I can implement these gates physically, I can approximate any unitary operations. Okay, therefore I will be able to implement any quantum algorithm. Okay, a quantum algorithm is simply a unitary operator. Okay, so let's talk about quantum speed up. You know, I have this kind of quantum phenomena that we don't have those quantum phenomena in classical computers. Can we use those quantum effects to have some speed up? Okay, so the idea is like this. We have the quantum parallelism. Okay, classically, if you want to do some parallel computing, you need to have several computers, and you divide a task into several small pieces, and you use a computer to run some pieces of the work, and then you combine all the results. This is the classical parallelism, right? But in a quantum parallelism, I can use a single quantum computer, okay, to have this quantum parallelism by using the effect of quantum superposition. Okay. Again, for example, suppose I have 2 quantum states, phi and psi. The superposition of these 2 states is a valid quantum state. Okay. So, for example, here, suppose we are calculating a function f of x. So x is an n-bit string. Okay. So I can prepare a quantum state like here, psi I have two registers. The first register is X. X runs from the index 00001 up to 1111. Okay, so here I prepare this superposition state. Okay, this is superposition. So, and the second register is in 0 state. Okay, and now a common computation can be described by a unitary operator. So I can generate the following output state. The first register is again X, but the second register becomes f of X. Okay, from the first state here to the second state here, you only have to run some unitary operation, right? This is a unitary evolution from the first state to the second state. Okay, so now in the second state, the second register has the information of f of X. Okay, but again, I have a superposition state here. X runs from all of the binary n tuple. Okay, so in this state, I have the information of all the f of X. Okay, using only one quantum state. Okay, so this is called quantum parallelism. Okay, so it seems that you can have quantum speed up from this state. Okay, however, there's no free lunch here. In fact, this is a superposition of these states. The superposition of X tensor f of X. Okay, if you want to retrieve one of the f of X, you have to do some measurement, and the state will collapse to a single output f of X. Okay. In general, we cannot retrieve all the results simultaneously. Okay. But if you retrieve the result one by one, then you don't have the speed up because you need to measure like 2, 3 n times, then you will lose the computing power. Okay. So to have a quantum speed up, you need to manipulate this state to have some benefit. Okay, this is a non-trivial part here. Okay, so people predict that we will have some quantum advantage after we have more than 50 qubits. Okay, so this is a plot of classical computing versus quantum computing. Okay, suppose the green line here is a quantum computer's computing time, running time for some task, and the x-axis here is the number of qubits. Okay, and if you want to simulate this quantum computer using classical computer, okay, you may need to some classical computing time. Okay, so when the number of qubits is below 50, we are able to simulate the classical computer. We are using the classical computer to simulate the quantum computer, and we can do it efficiently if the number of qubits is below 50. But if the number of qubits is above 50, the simulation time will have an exponential speed up. Exponential growth. Okay, so one day, if I have more than 100 qubits, I have some computing power beyond the capability of classical computers. Okay. So why is a 50 qubit quantum computer a milestone? Okay, because currently there's no non-classical algorithm can efficiently simulate a quantum computer. Okay, this is in 2016. If you remember what I mentioned before, that we use this H gate, S gate, and T gate, and the signal gate to run a quantum algorithm. Okay, so if the number of T gates is called a T count here. Okay, usually the T gate is the most difficult gate to implement physically. Okay, so if the number of T gates is more around 100 and number of qubits above 40 qubits, it becomes very hard to simulate. Okay. If you are interested in classical simulation of quantum computers, you may want to read this paper by Sergey Bravy and David Gossett. Okay, so if you want to have a quantum computer, we need more than 50 qubits, and we should be able to run a very long quantum circuit, meaning that we need to have a large quantum depth. Okay, otherwise, this kind of quantum machine can be simulated by classical using brute force. Okay, so recently, you may see a lot of advertisements from maybe IBM, Google, right? They claim they have 50 qubits quantum machine, or maybe 70 qubits now. Okay, so this kind of quantum machine is already available online. Okay, and they also show you the blueprint of their quantum machine and the performance of each qubit. Okay, all the parameters can be found online. So in 2019, Google claimed that they have a 72. This is 49 qubits machine, and they claim that they are able to use this quantum computer to demo some quantum supremacy, meaning that they have complete a task that is beyond the capability of classical computer. Okay, so what they do? Okay, so imagine that an n-qubit quantum circuit U on input 0 can be written as this superposition state. Okay, so if you measure the output state, you will get outcome I with probability the square of alpha I. Okay, so if you measure this state for several times, you get a distribution of I. Okay, a distribution of I. But this distribution is exponentially difficult to simulate by classical computing. Okay, as the number of qubits and the circuit depth grow, it is very difficult to simulate the distribution of this quantum circuit. Okay, so that's what they say here. Okay, an immediate application is use this kind of states to generating certifiable random numbers. Okay, so this is a circuit from the Google quantum computer. Okay, they are able to run like a circuit depth of 20. Okay, they have 15 qubits, and they are able to generate a distribution using 200 seconds. Okay, to produce 1 million samples, and they claim that if you use IBM's supercomputer, you need like more than 10,000 years. Okay, so that's why they claim they have demonstrated this quantum supremacy. Okay, and recently, in 2020, last year, China has demonstrated another experiment using photonic qubits. Okay, and let's also demonstrate another computational advantage using this quantum machine. But basically, this idea is like a quantum pinball. You see, there are many beam splitters within this circuits. Okay, a beam splitter is like a pinball, a pin here. Okay, if you hit a ball and laser probability go left and another probability go right. Okay, so it's like a beam splitter is like a pin here. So during these experiments, you can also have a distribution of something. Okay, and that distribution is difficult to simulate using classical computers, or difficult to calculate if you want to calculate the distribution, this is very difficult. So you may want to ask, what can we do with this kind of machine, right? But because doing this kind of distribution sampling seems useless, right? You need to find real applications, right? So this kind of quantum supremacy experiments is only used to demonstrate that we have quantum effects within these quantum computers, okay? So we need to consider a real task. For example, the most famous problem is the factoring problem, okay? The factoring problem. So we are considering this integer factoring problem. So we are given input a large composite number of L bits, okay? We want to find a non-trivial integer factor of L. So classically, no algorithm can do factoring in polynomial time, okay? Currently, the largest number of integer that can be factored is RSA 768, okay? 768. So RSA is the crypto system, okay? RSA 768 has been brought using like this kind of machine. If you use a single core 2.2 gigahertz AMD machine, you need roughly 10 to 20 operations to break this RSA 768. Okay, but if you use, so it takes roughly 2,000 years. Okay, so if you have like 100, maybe you use 1,000 this machine, you can cut down the time to 2 years, and then you will be able to break this RSA 768. Okay. However, if you want to have a better security, maybe you can increase the number to like RSA 2048, and probably that will be very safe. Using classical computers, you are not able to break those RSA 2048. In 1995, Peter Shaw proposed the first quantum factoring algorithm. So here we only need like all the L cube time with all the L qubits. Okay. So it means that for this RSA 768, you need roughly 1,000 qubits, and then you need like 10 to 9 operations to finish this quantum factoring algorithm. Okay, 10 to 9 operations. Okay. So compared to these classical algorithms, in classical algorithm, we need 10 to 20. Okay, we need 10 to 20 operations. But using quantum computers, you can cut down the operations to 10 to 9. Okay, so if I have a quantum computer that runs a quantum gate in a nanosecond, probably I can break this RSA system in minutes, right? So I need a quantum computer with more than 1,000 qubits that affords 10 to 10 operations. Okay, that's my goal. So I'm an engineer. I want to build a quantum computer with 1,000 perfect qubits, and the qubit need to be able to afford 10 to 10 operations. Okay, that's my goal. So in order to afford this many operations, each quantum operation should be accurate up to 10 to the minus 10, right? The error rate needs to be this slow because I need to run this many operations. Okay. So currently we have like 50 to 100 qubits in the recently, and a critical part here is that the error rate per gate is roughly 0.1%. It's like 10 to the minus 3. Okay, 10 to the minus 3. But my goal is 10 to the minus 10, right? My goal is 10 to the minus 10. Currently, I only have error rate 10 to the minus 3. Okay, with this kind of quantum gates, you are not able to run a circuit with more than 1,000 gates. Okay. So we need to have some other techniques to improve this. Okay. Even if you want to implement this error rate physically, it is very difficult to increase the precision to 1 order, maybe even 2 orders. Okay. So we need to use the idea of error correction. Okay. So one may also consider this hybrid algorithms. Suppose I have a small quantum computer and I have many classical computers. Can I have a hybrid classical quantum computer so that we can do things beyond the capability of classical computer? Okay, that's another direction, a hybrid of classical quantum computer. Okay, so Richard Josa, a very famous guy in UK, he raised the question whether any polynomial time quantum algorithm can be implemented with only log n quantum depths interspersed with polynomial time classical computations. Okay, because back to 2005, there are many algorithms that can be implemented in only log n depths, quantum depths, okay, including the factoring algorithm. So they are wondering whether we can suppress the quantum depths to only log n depths, okay? But last year, we have a paper disprove this result, okay? So large quantum depths really matters, okay? We need a quantum computer with a high depth, okay? So we need error correction to improve the performance of the quantum computer, okay? We need error correction. So it's classical from classical error correction codes, you know what is the error correction code. If I want to represent some data, I will use a larger space and I pick some data points to represent the original data, right? I introduce several redundancy. Okay, and in this larger space, the data has a certain mathematical structure so that I can use those mathematical structure to detect any errors on my data and then maybe even to correct those errors. Okay, that's the idea of error correction code. Okay, so I hope you are familiar with this. And okay, I will skip you this part. We want to extend the idea of error correction codes to the quantum case. Okay. Also, a very important part in error correction code is the decoding. For example, this is the 313 repetition code. I encode one physical physical bit in 3 bits. Okay. So here I use 000 and 111 to present logical 0 and logical 1. Okay. And if I find the data was in maybe 100, 010, 001, I will see there are something wrong here, right? And using some majority vote decode, I will see, oh, in fact, this is 000 with a higher probability, something like this. So to do a decoding, maybe I can use this majority vote, but in general, I need to be able to build a table such that I can locate what kind of error occurs efficiently. Okay, this is a decoding problem. So in general, if I have an NKD error correction code, that encode k bits in n bits with minimal distance d, it means that I can suppress the error from t to order p3 t plus 1. T is the half of the minimal distance, okay, using bounded distance decoding. So in general, the decoding problem is very hard. It is an NP complete problem, okay. If you go back to these papers, you will see the hardness of decoding, okay. So you want to have an efficient decoder for a certain code family. Anyway, so we want to extend these ideas to quantum case. Okay, so previously I mentioned that quantum states are continuous vectors, right? And the quantum evolutions are unitary matrix evolution. So you can imagine that maybe error correction is not possible because I have a continuous vector space, right? But there are some beautiful things happens, okay? We are able to discretization of the errors, okay? We say that a QB is a two-dimensional vector. So I can find the basis for the two-dimensional, 2x2 matrices. Okay, 2x2 matrix, I can find the basis called the poly matrices I, X, Z, Y, okay? These four matrices form a basis for 2x2 matrices, okay? So you can imagine that a unitary matrix is the linear combinations of these four matrices, okay? And the bit, the operations of this X is just a bit flip, like the classical case is a bit flip. The Z operator here will introduce a phase -1 to the cat1 state and do nothing on the cat0 state. Okay, so this phase flip is new. It's new from the classical case. Okay, classical, I only have this bit flip. In the quantum case, I have this phase flip. Okay, and the Y gate is simply a composition of the S gate and Z gate. Okay, so I can simulate the quantum circuit by this depolarizing channel. Okay, so with probability 1 minus epsilon, there's no error occurs, and with probability epsilon over 3, there's an X error or Y or Z error. Okay, so this is like the classical quaternary symmetric channel. Okay, so I only have like 15 minutes, so I cannot tell you much about how I get a quantum code, but I can define a quantum code like this. I define a billion stepwise group as from the n-fold poly group, and I will, for my quantum code, it is chosen to be a subspace of the NQB state space, such that the cover is the joint +1 eigen state of this group. Okay, so it means that for any element S in the stepwise group S operating on the cover will not change the cover. Okay, the eigenvalue is always +1 here. So if an error occurs, an error operator E occurs, and if E anti-commutes with these stabilizers, I will see that the eigenvalue is flipped like this. So I will be able to measure these stabilizers and to see whether error occurs or not. And using the eigenvalues of these stabilizers, I will be able to do some syndrome decoding, just like the classical case. Okay, so I will skip this part. So this is the most important message here. Okay, so binary quantum anchoring codes are in fact additive quaternary codes that are weakly self-dual. Okay, so you remember this word. So you can imagine that if I can extend the classical coding techniques to the quantum scenario to handle quantum errors. Okay, I simply need to consider these additive quaternary codes that are weakly self-due. Okay, so a desired quantum code has two important features. First one, feasible syndrome measurement. Okay, because the quantum states are very fragile, and it's very difficult to control the quantum qubits. Okay, you only want to involve a small subset of the qubits in a syndrome measurement. Okay, meaning that I cannot measure a bunch of qubits simultaneously. I can only have some qubit interaction, maybe like 3 or 4 qubits. If I want to measure more than 10 qubits simultaneously, that's very difficult in experiment. Okay, so I need to have feasible syndrome measurement. Okay, the second condition here is an efficient decoder. Okay, because the error rate is very high, right? So you need the decoding to be very, very efficient. For example, maybe you need to implement a gate in a nanosecond, but you need to do decoding more than much more faster than that. Okay, so that the quantum algorithm codes can work. So we would like to have something like this, the quantum low density parity check codes. Okay, because I will have only low weight parity checks, meaning that the syndrome measurement will be easier to implement. And in the classical case, I have the brief propagation decoding for LDPC codes. So I hope that will also true in the quantum case. Okay. So currently, this is the state-of-the-art quantum code architecture. Okay, this is called the surface code. So this is a two-dimensional surface. Okay, a white circle here represents a qubit. A white circle is a qubit. Okay, and a green cross or a yellow cross represent a syndrome measurement. Okay, so all of the syndrome measurement are of weight 4. Okay, or weight 3. They only involve 3 or 4 qubits. So these qubits, this syndrome measurement are easier to implement. Okay, and the minimum distance of the code is proportional to the length of this square. Okay, so currently, these surface code have the highest simulated error threshold about 10 to the minus 3. Okay, 10 to the minus 3 is roughly equal to what we can do in experiments today. So if the decoder for this surface code is the minimum weight perfect matching. Minimum weight perfect matching. The complexity of this minimum weight perfect matching is roughly order d to the 4. D to the 4. Okay, D is the distance of the code. D to the 4. There is a very big problem using brief propagation on this surface code. Okay. So the question: can we have good BP decoding algorithm for quantum algorithm codes? Okay, because BP have the complexity of a BP decoding is like d log d, right? D log d. So if I have a BP decoding for this surface code, I can have a very efficient decoder for this surface code, better than this one. Okay, this is the current state of the art. However, BP does not work for this surface code. Okay, I only have 10 minutes. I will skip. I hope you know what is mass passing and brief propagation. Okay. So the idea of mass passing is to pass what you know to your neighbors, and Yeah. Okay. So this idea can be used in decoding. We can have these data nodes and some checker nodes. These graphs are connected according to the peri-check relations of a code. Okay. So in the case of coding theory, we know that if this tenor graph has a short cycle, then the performance of the BP will be very terrible. Okay. If there are many short cycles in the tenor graph, the performance will be very bad. Okay. However, this is always the case in a quantum code. Okay, this is an example of the quantum code. Quantum code inevitably has these many Fault cycles. This is an example here. As you can see, there are so many Fault cycles. Okay, and this must be true because a quantum code need to be weakly self-dual. Okay, it needs to be weakly self-dual. It means that if I have to step by two pair checks, they are orthogonal. So they have to. So inevitably, there are many Fault cycles within this tenor graph. Okay. So let me check. So this is the performance using BP. Okay, on the surface code. Okay, you see the circle here is d equals to 5, and the star here is d equal to 17. But the y-axis here is the logical error rate. You see, as I increase the distance from the circle to star, the performance becomes worse. Okay, but you want to increase the minimum distance and have a better logical error rate, right? Like the case. So BP does not work for surface code. Okay. So recently, we have a new interpretation of the decoding problem as an energy function minimization. You can imagine that I have this energy function here, and the code, I want to find the code corresponding to the ground state of this energy function. Okay, and I can, using some idea from gradient descent in optimization theory, I can derive something from gradient descent. I will skip these details. And then, well, sorry, because I don't have time, I have to skip all of this part. So finally, I have this kind of quantum algorithms for quantum LTPC code decoding. In classical BP, sometimes you may want to scale up the message, okay? Because if the message is correct, you want to strengthen the message. If the message is wrong, you want to suppress the message. Okay, so there will be a scalar in front of the message. Okay. Usually one would like to have the messages to be smaller so that the BP will have a better convergence behavior. Okay, this is always the case in the case of coding theory. However, in the quantum case, we found that if we enlarge the message, sometimes we can jump out from some local optima to global optima in the energy topology. Okay, so that's a very important finding in our recent result. So I will skip all of these details, but you see there are some scalar here. I can change the size of the message. Yeah. Okay. There is also an neural level interpretation of our BP, but I will skip that and show you the. Okay, so this is our final result. On the left-hand side, originally, if you use the original BP, you will have performance like this, right? But in our BP, I have performance curve like this. If I increase the distance from d equals to 5 to d equals to 17 at this like waterfall curves here. Okay, so this is what we expect in BP, right? Okay. So this paper has just been posted on the archive in April. Okay. So this is a review article this year. They review all the important, most significant, important BP decoding strategies for the content LDBC code. Okay, so in 2020, we have this paper refined very propagation decoding of sparse graph plots in trace set. But in this paper, we are not still able to handle the surface code. Okay, in our recently 2 papers here, we are able to handle the surface code using the memory effects and the degeneracy in quantum codes. Okay, sorry, you need to understand more in quantum codes to understand this terminology. Sorry, I have to skip this part. Okay, so if you are interested, this is the currently development in BP. So let's back it to our factoring problem. Okay, so if we want to factor 1000 bits number using Peter Shell's algorithm. Okay, so previously we have estimated the resource we need. Okay, using surface code, assume that the get error rate is 10 to the minus 5. So currently the error rate is 10 to the minus 3. Okay, there are still 2 orders to get here. If I have a superconducting qubits quantum computer with get error rate around 10 to the minus 5, and I can use surface code to run these short algorithms, and in like 10 hours, I can break the RSA 1024. Okay, that's the idea. Okay, and the number of qubits here is like 10 million, and you need like 10 to the 19 gates. Okay, so this is a slide that Google announced in 2 years ago. Okay, so the x-axis is the number of qubits. The y-axis is the limiting error rate. Okay, so currently we have like a 72 qubits, right? So it's around 10 to the 1 to 10 to 100 qubits. Okay, so we are around this region, right? And the get error is between 10 to the minus 2 to 10 to the minus 3. Okay, so so we are in 2021. So in like 2015, this is the origin. Okay, so we spend like it takes like 6 to 7 years from here to here. Okay, our goal is here. The number of qubits we need is like 1 million or 10 million. Okay, and we want the error rate to below 10 to the minus 4. So this is a useful quantum algorithm code here. Okay, so we don't know how long it will take from here to here. Okay, I hope we can see this in maybe 20 years. I don't know. Okay, so this is the quantum effort worldwide. Okay, in 2021, they estimate the investment from the world in quantum computing. Okay, for example, Canada or UK here, Netherlands, Germany, China, Russia. So I'm a little bit surprised here in Taiwan. He said we spend like 8 billion new Taiwan dollars. Okay, but in fact, sorry, you cannot see this in Chinese. He said we will invest 8 billion, but in 5 years. Okay, in 5 years. So I have to divide this number by 5. Okay. Anyway, so you see Singapore, they spend a lot of money on quantum computing. They have a quantum computing center. Okay. So finally, I want to finish this talk by something you probably will see in the conference. Because we have new quantum resources. So we want to know what can we do with quantum resource. But usually we'll see in the conference, and you may want to say, do you guys just put the word quantum in front of everything, right? Because maybe if you're working on private information retrieval, and you will see things like quantum private information retrieval, right?
Yes.
Yeah. So what can we do with quantum resources? So in fact, we will have quantum everything codes to protect quantum state. We have quantum information theory to analyze the resource in quantum computing. Okay, we have quantum cryptography, quantum algorithms, quantum circuits. Yeah. Okay, so I will close by quoting Thomas Watson's word. He said that I think there's a world market for maybe 5 computers. Okay, he said this maybe more than 70 years ago, right? So I will put the quantum here. I think there's a world market for maybe 5 quantum computers. Okay, so we still want to do it, even if it's very difficult, and probably we don't have to. We have to wait more than 20 years, but we still want to have these quantum computers. Okay, so I'll stop here. I'll stop. Okay, I'll stop here.
Yeah, thank you very much for your talk. So any questions? If you guys. Yeah, so I do have a question. Can you go to your slide number 78 maybe? 78. Yeah, so I mean, I did it just to let me to have some motivation, but you say that we need some quantum error correcting code such that below than the error probability or error rate is 10 to -5, right? That's the goal.
Yes.
But do you know any, I mean, it's whether it's possible, right? Because for information theory, actually we can have some error probability low bounds and show that whether this kind of error probability is possible or not based on number of brackets. This is information theory can show this kind of things, right? I just wondering, okay, how about in quantum case? Because this is a goal, right? But what if the fundamental results cannot be achieved or not?
Okay, so in a Casio case, you see in a Casio computer, the error rate is around 10 to the -16. Okay, in a Casio computer, the error rate is very, very low, so you don't worry about that. But in a quantum case, you need to consider fault-tolerant quantum computation. Okay, so you have to design the circuits fault-tolerantly so that the quantum code can effectively correct the errors. Okay, because the errors usually propagates very quick in a quantum circuit through the 2-qubit gate. So you need to have a well-designed fault-tolerant scheme for the for each specific quantum algorithm code. Okay, for every quantum gate, you have to design a fault-tolerant procedure. So in that case, the resource will like multiply by 1,000 in this case. Okay, so and because I said that I need the logical error rate to be more than 10 to the -10, right? So I need an error correcting code so that I can reduce the gate error rate to a logical error rate around 10 to the -10. Okay, so I need additional resources, and so these numbers are estimated using those fault-tolerant schemes. Okay, so there are a bunch of stories behind these numbers. Okay. You cannot use information theory to do this estimation.
But whether it's possible or not, are there some people discuss this kind of things? I mean, because the goal, I mean, the goal of coding guys, the goal is, or content coding guys find existence, right? But what if they say this is impossible, or I don't know?
So the details of the code is very important, but in fact, we want to see the decoding performance. Okay, we want to see the logical error rate after decoding. Okay,
but even let's assume the Baxter decoding, for example, possible. What's the Baxter possible error probability can get for any possible content codes, for example? Do they have something these people also talk about, or?
Well, so usually there are a few content code families, and we can estimate the performance of these families.
Mm-hmm.
So they will have a curve like this. Okay. You can only do simulations on the performance of a code. This is the same event category, right? Because if you want to see the performance of an LDPC code, you have to run this kind of simulation. Okay. If you want to use Shannon theory to do the estimation, that would be far away from a realistic scenario. Okay.
Yes. But I mean, even a Shannon theoretical, if the performance is not getting there, then it's not mean that it's impossible to find such content code.
Yeah, that's correct. So in fact, we will also have things like quantum Hamming bound, like quantum singleton bound or first linear programming bound to have an upper bound on the distance of a quantum code. We also have those things.
Okay.
But here we are talking about this kind of service code. This code has a two-dimensional layout. We are more interested in this kind of codes because they are easier to implement physically because they have a two-dimensional layout. Okay. Yeah. So we have to discuss some specific code families, usually building from graph theory. For example, we may have some hypergraph product codes, okay, so that the code will have a two-dimensional geometry for implementation. Yeah. Okay. So, but you have raised a good question here. Usually, currently the most important coding problem in the quantum theory is the distance of a code family. Currently, most of the code family will have distance roughly the square root of the code length, the square root of code. So if I have a distance, if I have a length n code, the distance is roughly the square root of n. Okay, but recently, last year, a few guys proposed some very fancy constructions so that they can break this square root and gap, so that they achieve something like n3 minus 3/5, something like this. So they improve the result. Okay.
I see.
But this is still very hot topic. Okay, the paper I think has been published in maybe Fox or Stock last year. Okay.
Okay. Yeah, I think that's at least interesting. Yeah. So are they any? Yeah.
I have a broader question. Hi, can you hear me?
Yeah, I can hear you.
So I wonder if you have any educated opinion on those claimed near-term practical applications like It's quantum enhanced machine learning, for example.
Well, I will say, in my opinion, the quantum science is for some ideal things. I don't know if I mean, I will put in my how do I say this? So you see, there are some quantum computers available from IBM, okay, and those quantum machines are available for all the people around the world. If you are a college student, you can register it and use cloud service to access those quantum computers, and maybe you can simulate the simple quantum phenomena in their machine. Okay, some people may even do some experiments on the machine, and they can observe some very good quantum phenomena and publish in Nature or Science. Okay, but for this computing task, the current machine cannot meet what we want. Okay, and what's your problem again? What's your problem again?
Yeah, maybe repeat.
So in a current age, we can have some maybe quantum key distribution protocol. Okay,
Sure.
BB84, something like this. I can use a quantum key distribution protocol to have secure shared key.
But that doesn't
That's possible.
any quantum computation. That's
Yeah, but if you go to computations, I don't know any improvement using quantum computer. And recently, there are many quantum machine learning papers. Okay, you may have heard quantum machine learning papers.
Yes.
Most of those quantum machine algorithms are based on some quantum algorithm called HHL algorithms, because that algorithms can improve the calculations of solving linear systems. Okay, so previously, there is a very famous quantum algorithm called the quantum recommendation system. Okay, based on the HHL algorithms, so that can improve the recommendation system. Okay, but usually those kind of algorithms require a strong assumption that you have a quantum register. Okay, you need to have a quantum register to store the messages, right? So if you have suppose you have a bunch, maybe for example, if you have 1 million classical data, if you want to use a quantum machine to handle that, you need to transfer those data to quantum data. Okay, and that's very difficult. And because for example, you have qubits, but your data may be some real numbers, complex numbers, and you want to transfer those data to a quantum machine, to a quantum register, and handle that. Usually, those quantum algorithms will make a very strong assumption there. Okay, and there's another type of quantum machine learning. So, as I mentioned previously, I said that using a quantum computer, you will have a higher dimension of state space, right? Because the dimension of a quantum state grows exponentially in the number of qubits. So there's another direction of machine learning. They will use a classical machine learning protocol, but they will switch one of the function to a quantum function. So for example, in the classical machine learning, there is a kernel function, right? Kernel function. They will switch that kernel to a quantum kernel, so that the quantum kernel will handle the information in a much higher dimension. Okay, and they will demonstrate that. For example, if I have a 3-qubit kernel, maybe the performance is better than like a 100 bits classical kernel, something like this. Okay, but there's no theoretical proof for this quantum advantage. I don't know. Okay, so what I saw here is people will replace the kernel to a quantum kernel and just do as what you do in the classical case. Yeah.
Thank you.
I don't know if there is any theory to support that.
I see. Yep. So are there any other questions? Yeah, okay. Then maybe we thank speaker again. Thank you.
Yeah.
Thank you. Thank you.
Okay.
Yeah, okay, thanks.
Thanks.
Thank you.